Very good afternoon to all. This is K.R. Sendil Murugan, Assistant Professor, CEC Department. Welcome you all for the ATAL Academy sponsored 1 week FDP on deep learning for visual computing. So day 4, session 10 on data-driven techniques in visual computing. So it's a great honor for me to introduce our resource person of this session. She is none other than Dr.S.Sika, OK, Assistant Professor, Senior Grade, Department of Computer Science and Engineering, Amritha University, Coimbatore. Welcome you, ma'am. She received her B.Tech degree in Information and Technology from Calicut University Institute of Engineering and Technology, and M.Tech degree in Computational Engineering and Networking from Amritha University, as well as she received the PhD degree from Amritha University, Coimbatore. And she has received a Young Woman Educator and Researcher Award from National Foundation for Entrepreneurship Development. Her research interest includes the computer vision and artificial intelligence. She has published a good number of papers in SAI indexed journal. She mainly focused on providing the solution to computer vision problems in various application domains, including the healthcare and surveillance, etc. With this short intro of our resource person, I would like to hand over this session to Dr.S.Sika, ma'am. Ma'am, please take over, ma'am.
Thank you, sir. Hope I'm audible.
Thank you, ma'am. Yes, ma'am. Yes, ma'am. Audible.
Yeah. So first of all, thanks to the entire organizing team for inviting me to handle a session in this ATAL workshop. So shall I share my screen?
Yes, ma'am. Yes, ma'am.
So hope my screen is visible for everyone.
Yes, ma'am. It's visible.
Okay, thank you. So yeah, good afternoon once again. So in this session, the current session is all about data-driven models for visual computing. So I would like to, proceed in the direction where I'll be sharing a few views on convolutional neural networks for the visual computing aspect. So this is the agenda of my session. So as you all know, getting the right question is the key to getting the right answer. So I have come up with few questions, and I'll try to, give probable answers for each of this, which ultimately gives you an insight on data-driven model for visual computing, especially convolutional neural network for visual computing. So we'll be starting with what is exactly mean by visual computing, and then what is data-driven modeling. These two are the two buzzwords of my session title. And then we'll also look into why data-driven modeling is so important in this era of digital data. And then we'll slowly move towards the importance of having data-driven solutions, especially for computer vision, real-world problems. And then we'll have a discussion on deep learning. I hope for the past 3 days, you are exploring this particular aspect, deep learning. So how deep learning is important in data-driven models, because deep learning architecture itself is a data-driven model. So what is deep learning, why and how learning happens in deep learning? Just a small introduction, though you already know this concept. And then we'll have a short introduction to convolutional neural network, because this is one of a very specific deep neural architecture, which is just designed to handle visual data. And then I would like to close my session with a hands-on case study on a high-end computer vision application, that is object detection and instance segmentation. So that's the agenda of the entire session. So I'm a believer of this phrase, a picture is worth 1,000 words. So as a computer vision aspirant itself, I believe that if you are seeing something, your brain is able to extract more useful and optimal insights out of it. That is why, because human brain is designed in such a way that more than 90% of the information that is gathered by the brain is coming as visual data. So I've tried to include more visual content in my material so that you all will get a good insight of what is supposed to be, delivered today. So with that, let us start with the first question of the day. What is visual computing? So as you all know, you are all immersed with large amount of data. So whenever I say data, I just meant the digital form of data. So with the large volume of digital data, which is available these days, it actually demands for certain kind of automatic visual representations which can make the people to understand complex information out of it, or maybe to extract useful insights out of it. So there comes this visual computing. So visual computing can be considered as a field of computing that deals with acquisition or maybe analysis and synthesis of visual data. Visual data, in the sense, it can be a combination of images or videos primarily through the use of different computer science algorithms, obviously. So the primary objective of visual computing is which allows us to control and interact with activities through the manipulation of visual content. So let us see what are all the major application domains of this visual computing. The first one is computer graphics and animation, and then comes complex system simulations, and then comes computer vision. So let's see each of this in detail. So when it comes to computer graphics and animation, it's all about, say, a mix of programming stuffs, mathematics, and maybe a few visual creativity, using which you can simulate something which is very interesting. So maybe an example is a human face simulation as shown in this PPT. So the primary objective of this visual graphics aspect of visual computing is to produce interactive experiences, especially in augmented reality and virtual reality. Moving on to the second probable direction, that is complex system simulations, as I already told, a picture worth more than 1,000 words. So if you are looking to provide a computer vision solution to a real world problem, and if you have access to a real world scenario as such, then it's very easy for us to propose an optimal solution. So wherein the simulations, all the kind of simulations will come into picture. So normally when it comes to a complex system simulations, graphical hardwares will come into pictures like GPU, graphical processing units, which are primarily used to provide scalable software solutions for, say, science and various engineering problems. So one such simulation is shown here, which is the simulation of pedestrians and traffics in a city area. Moving on to the third aspect of visual computing, computer vision. So today's session is more concentrated on, aligned towards this computer vision aspect of visual computing. So when it comes to a computer vision research, so mainly it focuses on solving real world problems, say object detection, recognition, human detection and tracking, or scene understanding, etc. So that's all about visual computing. So we'll be moving towards the computer vision aspect of visual computing. So next comes data-driven modeling. So let's see what does exactly mean by data-driven modeling. So as the name indicates, the data-driven models primarily tries to collect data and analyze data, and it tries to extract some insights out of it. So these days, the term or the kind of data-driven modeling gain, more, they're becoming more famous and against the classical algorithms. That is why, because using this data-driven models, what we all require is relevant data, access to relevant data. So these data-driven models primarily, they analyze the data to extract correlations or connectivity between different system state variables, say input and output variables. They also help us to learn some unforeseen patterns from the data, ultimately, which can be, used to give some solutions to a real world problem. This can also be used to perform predictions without the availability or any prior knowledge about the system, which is very important. So if you are, if you have decided to proceed with a data-driven model solutions, and then you don't have to worry about the system at all. What you have to deal with is, do you have access to relevant data? So that's why data-driven modeling is so important because as we all know, we are all, in this era of digital world, we are all immersed with large volume of data, which includes both structured data and unstructured data. So when it comes to unstructured data, most of the data which is in the form of visual content, everything comes under unstructured data. So just to showcase how much data we have in our hand, I just have a pie chart from Statista. So the statistics is from 2020. It actually shows the amount of data which is being created on the internet within a minute. Okay, it's just for a single minute. So according to their survey, more than 500 hours of video is getting uploaded by users into YouTube. More than 3 lakhs of stories in Instagram. So whenever it comes to Instagram, it's completely unstructured in nature. So you'll have a mix of text, probably a mix of text, images, and videos, etc. And because of the corona, the current pandemic situation, everyone is in a work from home mode. So more than 52,000 users are connected through Microsoft Teams or any other platforms like Google, say Meet. So in fact, currently you, me, we are all actually, acting as data providers because we have connected through internet and the session is getting recorded. So somewhere it is getting, stored. So all of the statistics will give you an understanding of the data availability. So if you wanted to proceed with data-driven modeling, the only requirement is data. And now you can see data is everywhere and data is everything. So when it comes to visual content, more than 90% of the visual content is coming from social networks because millions of photos and videos are getting uploaded by every second and every day to the various social network platforms, say Facebook, Instagram, YouTube, etc. Let's move towards computer vision. So as I explained, the one factor why we can go for data-driven solutions for computer vision problem is because of the availability of unstructured visual content in the internet, because millions of photos and videos are getting uploaded every day, every second. When it comes to the other aspect of computer vision, okay, rather than dealing with natural images or videos, okay, so you may be interested in medical image analysis. So in that domain also, because of the advancements in various imaging technologies, say like CT scan, PET scan, MRI scan, a lot of medical images are also being populated, and most of these contents are freely available, openly available. And the third reason could be the free unlimited cloud storage services provided by various companies like Google, GCP by Google, and Amazon Cloud Azure by Microsoft. So most of these cloud platforms allows us to, or gives us a space where we can store data. And also they have their own networks, especially when it comes to GCP, Google Cloud Platform, and other platforms as well. They have their own AI frameworks, which allow the users to play around with the data with various AI or artificial intelligence models. So if in case, if you are interested to proceed with the medical image based problems, I just gave a repository, Cancer Imaging Archive. So it's a huge repository where you can see huge data sets. They have different CT scan data sets, X-ray images, lots of microscopic images are available, and with their prescribed or their papers also. So you can align your research problem and can find out the best possible data set for it. So because of all these reasons, so currently we have access to a huge volume of data. So it's very important to proceed with a data-driven based solutions because it's very easy to implement. You don't have to come up with any prior information about the system. You don't have to have a mathematical modeling of the system. All you need is data. So with all this, it's easy for us in this era to proceed with data-driven models, especially for vision-based applications. So given that, let me just explain few of the interesting computer vision challenge. So driverless car or automatic car, which is being most, well-known example and most, it's a kind of phase changer of computer vision applications. So when it comes to a driverless car, the car has to have some human-like intelligence. It has to decide when to stop, when to start, or how to adjust the speed. It has to recognize different types of objects real time. And then another example is dense image captioning. So with the advent of this driverless car, it also had impact on many other computer vision, open research problems. One such is dense image captioning. So dense image captioning can be considered as a successor of classification. So when it comes to classification, all you have is you'll have an input. Say this is your input, and you'll come up with a single label. So that label will tell what that particular class is. Built upon that, the next level was object detection. So given an object, okay, the models will try to detect multiple objects, say cat, skateboard, etc. So with this object detection, researchers have moved towards give a caption to an image, say a cat riding a skateboard. So it's a very abstract caption. And then people have moved towards dense captioning. So dense captioning is something like a human-like captioning. So as a human being, if you ask me to give a description about an image, based on my previous experience, I can even give a story to you, right? So everything is based on the kind of knowledge or the kind of intelligence that I have. So people have tried to transfer the human visual intelligence to the machine, and they've tried to incorporate some semantic information as well. So instead of just giving an abstract view of the content of the image, they have just give semantic information, say like orange spotted cat and maybe skateboard with red wheels. That's another example. And the next example is instance segmentation. In fact, today we are going to have an overview of this instance segmentation application. Again, it can be considered as a successor of classification. So ultimately, this is your object detection. So whenever you see an object, whenever you see an image, the object detection models will tell you the location of the object. Okay. So when it comes to the next level, that is semantic segmentation. Okay, you can see there are 4 objects. The object detection model very well can say that 4 objects. Out of these 4 objects, okay, you have 2 different categories. Like you have a dog and 3 sheep. So that's where the semantic segmentation comes into picture. So it will locate the object. It will also tells you what kind of object it is. Going to the next level, that is instance segmentation. Though you have 2 categories of objects, your semantic segmentation won't tell you in each category how many instances are there. It cannot tell, say, there are 3 sheep and 1 dog. What semantic segmentation can say? There are sheep and a dog. That's all. But when it comes to the next higher level of application, that is instance segmentation, for each of the object instance, you will get a mask. So ultimately, you'll get the location of the object. You'll get to know the category of the object. You'll also know how many objects are there. So I can easily say from this instance segmentation output, I can easily say there are 3 sheep and 1 dog. Which move towards another interesting application, which is visual question answering system. So here the model is, expected to give answers. So given an image, you can ask a question to the image. Your model should give an answer. Say, for example, what is the mustache made of? Then your model should be able to say made of bananas. Or maybe how many slices of pizza are there? Then it has to exactly count the slices and it has to give the answer. Again, it's a kind of, we are moving towards human kind of intelligence. So all these kind of, these are all open research problems. Still, you can find out infinite number of problems which are yet to, get a proper solution. Definitely healthcare. So as I told, you have access to large volume of medical data, and you can use them to help the doctors to perform a better diagnosis and detection of various diseases. So for solving all of these real world problems, definitely you cannot proceed with classical computer programs. You have to proceed with artificial intelligence. So I'm not going to explain this artificial intelligence in detail because you might have various session on this particular buzzword, artificial intelligence. So you can consider it as a combination of machine learning, deep learning, expert systems, natural language processing systems, speech systems, and vision systems. What we are going to look today is more into deep learning. So when it comes to machine learning, AI is a superset, and then comes machine learning, and then comes deep learning. So machine learning, in fact, it uses algorithms to parse data and learns from the data and make decisions based on what it has learned. So our subject of interest is visual content. So it's completely unstructured in nature. When it comes to machine learning models, they expect some kind of structured input. So the first step would be, if you have an unstructured data like this, images and all, you have to have a feature extraction technique or a model. And using these features, your ML model will learn and then perform a task. When it comes to deep learning, okay, deep learning does not require any feature extraction. So deep learning can be defined as a subfield of machine learning, which is actually inspired by, say, biological neurons of brain. So what we are trying to do is we are trying to mimic human brain. So you will have a set of neurons stacked over one after another, different layers. They all will be connected to each other, and they are trying to learn weights based on the data that you're going to provide. Now, yeah, we had machine learning. Then why we have to move forward towards deep learning? So the reason is data. Okay, so we have large volume of data with us. So as the volume of data increases, okay, it came to know, see, it's something like your machine learning technique. Say, for example, no matter how much you optimize, no matter how much you tune your parameters, it seems to be, your performance seems to be become inefficient in terms of accuracy. But in the case of deep learning is all about data. So if you have access to relevant data, the more you have data, the more accurate your model will be. So that's why ultimately we have moved from machine learning to deep learning to solve real world problems that we have just discussed in the previous slide. So now let's see how learning happens in deep learning. People used to say deep learning is a black box. We don't know what exactly is getting learned inside these layers. To an extent, it is true, but fortunately, these days, researchers have started exploring to visualize what is getting learned in the intermediate layers of various deep learning architectures. So ultimately, the learning happens in deep learning in an incremental way. So I have two use cases here. So let me start with the visual use case itself. So the use case is face recognition. So as I told, it's an incremental kind of learning. So which means for your deep neural network, okay, the initial layers try to learn low-level image features. Say, for example, edges or textures or shapes. When it comes to the middle layer, okay, it tries to learn some complex level of features or shapes, say eyes or mouth for the face recognition example. And then when you move towards the deepmost layer, okay, where the neural net architecture tries to learn some application specific features. In other aspect, the other synonymous, you can see that, okay, the lower layers will learn letters first, okay, middle layers will learn words, and then your deep layers will learn sentences. So ultimately, when it comes to any deep learning architecture, okay, the learning will happen incrementally. So when it comes to computer vision applications, so the problem is with the input. So our input is going to be either a one-dimensional image, if you're going to deal with a grayscale image, or you may have a three-dimensional image if you're going to deal with a color image. So color image in the sense you will have three channels, red, green, blue primarily. So it's going to be a three-dimensional matrix. So the problem with this visual, when we are going to solve visual or a computer vision based problems, or when your input is a visual content, or when it is an image, the primary problem is the computational cost. So when it comes to a very small image, say 250 cross 250, okay, it comes around 62,000 plus, pixel values. So we cannot actually, proceed like given an image, you vectorize the image, and then you will feed that one-dimensional vectorized image representation into a normal neural network. It is going to be very tough because what you have going to have here is, okay, it's going to be 62,000 plus neurons because you have that many number of pixels. So you cannot proceed with a normal neural architecture when you are dealing with visual content. Definitely you need an alternative where this convolution neural networks came into picture. In fact, with the development of convolution neural network, this was a phase changer of computer vision research community. So what this convolution neural network will do? So convolution neural network, the architecture is designed in such a way that it can take a matrix as the input. So the input need not be a one-dimensional vector. It can be a 2D vector. Okay, 2D vector in the sense it can be a matrix. So that you can push your image as such into your convolution neural network. So ultimately, this convolution neural network will be able to capture spatial and temporal dependency. So we can consider this convnet as a combination of a feature extractor followed by a classification layer. So primarily it performs two tasks: feature extraction. The feature extraction is carried out with the help of convolution layers and pooling layers. I'll explain those layers in detail. And then ultimately after stacking different convolutional and pooling layers together, the final feature vector will get flattened. That is your feature vector. The feature vector is ready, which is then given to fully connected layers to make it, to have it as a nonlinear relationship, and then given to the output layer. So this is a basic architecture of convolutional neural network. So you have your input ready here. Input is an image. So every pixel matters. So you don't know which pixel gives you, or which pixel is more important to perform a particular task. So every pixel counts. So this pixel is given to a convolution block, okay, followed by pooling layer. So you will have a mix of convolution and pooling layer together. And finally, once you are ready, you have done, okay, you'll flatten it and then you'll map it to various fully connected layers. And then ultimately it will give to your output layer. So the output layer will be different. You can decide on what kind of output layer you can append here based on the kind of application. So if it is a classification, you can proceed with softmax layer. So I hope you have a standalone session on convolution neural network probably tomorrow. So I won't dig deep into any of these concepts, but yes, still we'll have a short discussion on each of these modules. So this part I already explained. Okay, why convolution neural network? Because your input that you're going to deal with is an image. It can be either a one-dimensional image or a three-dimensional image. You will have three channels. The dimension in the sense three channels. So the data is going to be computationally intensive. So the primary objective of this convolution neural network is to reduce the image into a form which is easier to process, which means you have to have a pixel-wise computation. So let's see the first layer, that is convolution layer. So this convolution layer ultimately mimics the normal filtering operations in your classical image processing domain. So whenever it comes to a filtering, you'll have a kernel, associated kernel, and what you'll do, you'll just convolve your image, input image with the kernel. So you'll have a window size. So you will pass the kernel pixel by pixel, and then you will do the processing. So this convolution also do the same thing. It tries to take a kernel, and the kernel will be translated through or convolved across the image, and ultimately it produces some results. So I just have an example. So assume this is my image and my kernel is this. It's a 3 cross 3 cross 1 matrix, 1 0 1 0 1 0 and 1 0 1. This is my kernel. And how this convolution happens is your kernel will shift. It will start from here. Okay, your image pixels are convolved with this kernel. You'll get the results, and then it shifts to the right. So in this particular example, the kernel shift 9 times. Now this shifting is very important. It actually depends on the stride length. So the stride length is nothing but it's the number of pixels that shift over the input matrix, which means if the stride is 1, we move the filter to 1 pixel at a time, towards right, and then hop down, and then again move towards right. If the stride is 2, we move the filter to 2 pixels at a time. So that is convolution operation in detail. So you have a filter which starts from left and move towards right till it passes the complete width, and then it hops down, again start from the left, move towards right. Then comes the stride. So this is the example. Left one is stride 1. So when you see this, kernels are shifting 1 pixel towards right, and then 1 pixel down, and then again 1 pixel towards right. But when it comes to stride 2, the right hand simulation actually shows stride 2. So there you can see this is your kernel. Okay, the top view, this is your kernel. This is your input image. So when your stride is 2, what is happening is you are skipping 2 pixels. Okay, you are skipping 2 pixels to the right. And then hop down, again 2 pixels down, and then you will move towards right. So that is stride. So the next layer is pooling layer. So the primary objective of this pooling layer is to reduce the spatial size. Okay, so you have a large image. So if it is a high resolution image, you can even have 2048 cross 2048 image. It's a very huge image, computationally very complex because we are doing a pixel wise operation. So in order to make it computationally more effective, one naive solution is to reduce the spatial size. So that's where this pooling layer comes into picture. So the primary objective of this pooling layer is to reduce the spatial size. So this will decrease the computational power ultimately to process the entire data. So there are two types of, two famous pooling operations. One is max pooling, the other one is average pooling. So if it is a max pooling operation, so you will have a window size of interest. From this window size, you'll take the maximum and replace it with the output. So here also 30, and from this window it is 112. From this window it is 32. So initially the input was a 4 cross 4 matrix. This is your image. And after max pooling, it becomes 2 cross 2. Okay, just a half with respect to the number of rows and number of columns. Similarly, average pooling, the only difference is instead of going with the max operation, you'll proceed with the average operation. So the first layer is convolution, and then followed by pooling. You'll stack several convolutional blocks together, and then in order to perform, say suppose the task is classification, you will flatten the convolved feature, and then which is then given to a fully connected layer, okay, which is then given to your output layer. So output layer depends on the kind of application that you want to perform. So if it is a classification, then you will have to you can go with softmax layer. So let's see. So that's all about the basic architecture of convolutional neural network. So hope it is clear why we have to move from machine learning to deep learning. And again, when it comes to deep learning, why convolutional neural network when it comes to visual content, and then what are all the basic aspect or basic architecture of convolution neural network. And then I would like to introduce you few classical networks. Still, I'm not going to go deep into any of these architectures. I just wanted to show you how everything happened. So the first class is lennox, where it all started actually. So it is actually known as the first convolutional neural network, which was built in 1980s. The primary objective, the goal of this particular neural network, lennox, was to recognize handwritten digits for a grayscale image. So according to the old version of this lennox, they were designed it in such a way that the input was 32 cross 32 cross 1. So this 1 actually represents the number of channels. So the initial model was meant to perform a handwritten digit recognition from grayscale image. So when it is a grayscale image, you will have only one channel. So the input size was 32 cross 1, and they used 5 cross 5 filtering. The size of the filter was, or the kernel was 5 cross 5 with stride 1. With stride 1, followed by 2 cross 2 filters, and then max pooling. Though it was implemented in 1980s, we can see several modern versions of lennox. So initially, in the first iteration of lennox, they were having a single output, and then they modified it as 10 neurons in the output. So this 10 neurons represents 10 classes ultimately, numbers from 0 to 9. And then few of the modern networks, they have almost 1,000 times bigger and deeper than the original architecture. So lennox was considered as the first CNN built ever. The next breakthrough was when it comes to alexnet. So alexnet, the idea was deeper is better. From that concept, they have come up with a very deep neural network compared to lennox. Lennox was just 5, in depth in 1980s when they developed that. So alexnet, the idea was deeper is better. So it is the first CNN model which implemented on the graphical processing units, GPUs. The main difference between alexnet and lennox was lennox had used maybe 2 types of filters, 5 cross 5 and 2 cross 2. But this alexnet architectures, they have incorporated different kernels of different sizes, 11 cross 11, 5 cross 5. So this is 11 cross 11 with stride equal to 4. And then you have 3 cross 3 with stride equal to 2. You have 5 cross 5 with same striding. So all those things. So it was a combination of kernels of various sizes. And also compared with lennox, there were more number of channels and the network was very deep in nature. Another speciality of this alexnet was it was the winner of ImageNet classification challenge in 2012. So that's why this alexnet is known as the phase changer of convolutional neural network. So when it comes to ImageNet image classification, what is ImageNet? In fact, it's a large data set of annotated photographs, and it's an openly available data set, which is purely meant for computer vision research. So these days also, this computer vision community is considering ImageNet as one of the benchmark to validate and to test the models. So that was AlexNet, all about AlexNet. And next comes VGG16. So initially in the AlexNet, they try to use different kernels of size 11 cross 11, 5 cross 5, and 3 cross 3. So all of the idea was, if you have a bigger receptive field, and then you will get more insights out of this image. But VGG16, it's all about, they have tried power of smaller filters, especially the power of 3x3 convolutions. So with this, they were able to simplify their model, but they were able to come up with a better accurate model. So the idea was to break down all the high receptive fields like 11x11, everything into as a combination of 3x3 convolutions. So according to the VGG architecture, the authors claims that multiple 3x3 convolutions stacked together, they're actually capable of replicating bigger receptive fields, say 5x5 or 11x11. So that's all about VGG16. So everything started with lennox, and then alexnet came into picture, where they have tried different receptive fields, in the sense different set of kernel sizes. And then VGG16 tries to simplify the model by reducing everything as a combination of smaller convolution operations. But the problem with these three kind of networks, the problem was vanishing gradient. As you all know, okay, since the learning happens incrementally, okay, it learns from its mistake. A neural network learned from its mistake. So you will push your input data with a label. Your neural network or your CNN will predict what it is. You'll have your actual label. You'll calculate the error. And the error is getting back propagated. So the back propagation will start from the deepest layer, that is a final layer, and it will traverse towards the initial layer through the middle layers. So when this happens, the problem is the gradient. The gradient may vanish. So whenever I say gradient, here I meant the error gradient, which is nothing but the direction and the magnitude calculated during the training of your neural network. So whenever you have a very deep neural network, vanishing gradient is a problem. So though you have a deepest neural network, okay, with respect to its accuracy, because it can learn more complex features or more application specific features. So increase the deepness of a neural network is good, but at the same time, this particular vanishing gradient problem may arise. So as a solution to deal with this vanishing gradient, a ResNet model was developed. Again, it was a phase changer within the computer vision community. So ResNet, the idea is they had short connections. So if you have a very deep neural network, say this is a 152 layers of ResNet network, instead of passing the error gradient across all of the layers, they had skip connections. They have a separate path through which the gradient can proceed towards the initial layers. So the problem with this vanishing gradient is your initial layers, the weights will not get adjusted. If the error will not reach the initial part of your layer, those layers weights will become stagnant. So that problem was actually got resolved with the skip connections. So that was ResNet. So with all of these kind of networks that I've just shared, lennox, alexnet, VGG16, or be it ResNet, most of them are very good at performing naive applications like, say, object classification and maybe prediction to an extent. But with the self-driving cars, which is a well-known, a most spoken computer vision application. So there, you cannot actually proceed with these set of classical networks. Why? Because most of these classical networks, they have a very trivial architecture where you have a set of convolutional operation which act as a feature extractor, and that features are used to perform, say, a classification. But what we need is something like this. So this is a starting point of, say, the self-driving car, where you have to perform object detection or maybe instance segmentation. because object detection is very important. Say, for example, assume that there is a short turn in the road ahead, and if the system just draw a rectangular box around the road, then the car may not be able to understand whether to turn left or to turn right. So in order to make real-time decisions, in order to make critical decisions on the run, you cannot proceed with the normal CNN. Okay. Whenever it comes to object detection, yeah, it works very well with classification, because ultimately classification expects a single label. But when it comes to object detection, you will have multiple objects. So you have to have multiple, labels. So the output is not consistent. It is varying. So from one image to another image, it is different. So when it comes to the the so-called real world application, it is highly dynamic. You cannot predict what is going to happen in the next moment. Exactly same. So you cannot have a very static neural architecture to solve these kind of high-end image processing, not image processing, computer vision applications. So people have come up with a little bit more complex architectures. So it can be considered as a variant of your normal convolutional neural network. So one such family that I'm going to introduce is RCNN family. So RCNN stands for region proposed convolutional neural network. Okay, RCNN. So this RCNN family has so many variants. So the first variant is RCNN itself, that is region-based convolutional neural network. So here the idea is you'll have an input image. The RCNN tries to extract regions. So your image may have different regions, and say this part may belongs to, say, object 1. The very next part or region may belongs to object 2, so and so. So, but you don't know how many objects are there. So it's highly dynamic. So this RCNN, the idea was you take an input image, first you extract region proposals. So the region proposal is nothing but you traverse across your image and find out the region where you can find out some object. Okay, you propose a region which has some objects in it. So they have actually used a naive selective search algorithm to extract around 2000 regions from the image. So they just come up with 2000 image regions, and these image regions may have some objects. And those image regions, similar image regions, were wrapped around, which is then given to a convolutional neural network for extracting features. And again, it's actually like a normal classification. So instead of giving a single label, what they have done is it's a region-wise operation. You find a region, push to a CNN model, find what kind of object it is, go to the second image region of the same image, second region of the same image, you push that region along into a convolutional neural network, and then say what kind of object it is. But the major problem, this was actually, it was a successful model, because instead of giving a single label, they were able to provide or they were able to detect all the objects that are available in the image. But the problem with this RCNN was the computational complexity, because it took around more than 50 seconds, okay, in the testing environment. So they themselves did not did not proceed it with the real world application. And hence they have moved towards the second aspect, or the second version of the same model, that is fast RCNN, which is also from the same, author. Okay, so the fast RCNN, the only difference was, instead of feeding the region proposals, you take a region, feed it into CNN, take the second region, feed it into CNN. So if you have 2000 regions, you have to will have 2000 forward movements. you will forward 2000 regions separately into your convolution neural network. But that was a time consuming task. So what they did is, instead of feeding the region proposals to a CNN, the entire input image was first given to a CNN. So CNN will extract the feature. The convolutional feature map that comes out from the CNN was then given to a region proposal, which means the selective search, they just changed the order. Initially, it was your input image, selective search, convolutional neural network, and your class prediction. Fast RCN, what they did, they just changed the order. Input image, convolutional neural network, which will produce a convolutional feature map, which is then given to a selective algorithm to select the region proposals, which is nothing but a region with an object, and then given for the class prediction. But still, fast RCNN, since they have used this selective search, still it was not applicable for the very real world applications like automatic or maybe driverless car. And then that's why they moved towards this third category. All of these categories with the corresponding paper and code is available in this slide. I'll share the slide so that you all can access this. So next comes this faster RCNN. So the only difference between fast RCNN and faster RCNN was this faster RCNN, instead of selective search, they did not use selective search at all. They have come up with a new model, that is region proposal network. So ultimately, this RCNN family, RCNN, fast RCNN, and faster RCNN family, they were able to perform more accurate object detection along with the bounding box labels. Bounding box in the sense the coordinates for the bounding box. So the object detection was very perfect. But what required was the instance segmentation, which means you have to locate the object, you have to segregate each instance of the object, and for each of the instance, your model should be able to say, okay, with respect to a confidence level, say 90% confidence, this is a person. A 90% confidence is a car. So that kind of masking is required, a segmentation mask. So that actually leads towards the development of a new neural network called MRCN. Okay, so MRCN stands for mask RCNN. So it is actually, it's a successor of FRCNN, that is faster RCNN. So this is the architecture of MRCNN. So ultimately this part is purely your faster RCNN architecture. So you have an image, first you will apply convolution neural network, and then you will find the region of interest. Till that it is the same. The only difference is, along with this region proposals, an additional layer, convolution layer, is added to perform the segmentation, which means this particular MRCNN model will first compute the region of interest, and for all the region computed, it will calculate an IOU value. I'll explain that, what is IOU, intersection of union. And then with a confidence score, if IOU is more than 0.5, they will consider that as a region of interest, and then they will come up with a mask. So ultimately, your MRCNN will gives you an output where the object detection will happen, and you will have a mask, a segmentation mask that comes out of it. So let's see this MRCNN in detail. I'm moving towards the Jupyter notebook. Is it visible? Jupyter notebook?
Yes, ma'am.
Okay. So let's first see the MRCNN modules first. So you'll have a backbone network. So normally the backbone network will be either can be ResNet 101. It's one of the classical neural network that I've just explained. So normally this backbone network is used to extract features from the image. So it's just a convolutional neural network. So it is used to extract convolutional features from the images. So ultimately these features are passed towards the next layer. So your next layer is region proposal network as per your faster RCN model. So this region proposal network, it actually tells you a region which has some objects. So ultimately the result from RPN will be the region with some object. So first convolution neural network is applied, which will produce some feature map, which is then given to an RPN network, which will tell you, okay, in this feature map, what are all the positions, possible positions or regions where you can find a object. And then region of interest. So from each of this region, every region will be of different sizes. Okay, so to handle a different size, data is again, it's a problem. So this region of interest, the goal of this region of interest is to make every region to a same equal size, and then which is then given to the segmentation mask. Now, when it comes to the generation of segmentation mask, it is the only addition of MRCN when it compares with your faster RCNN. What you have to do is they will calculate an IOU value. So IOU is the intersection or union. So let me explain with an example. So this is my example. So assume this is my ground truth label. So ground truth label, in the sense, for training, you need to have ground truth label, right? So here the expectation is a masked output. So the ground truth label, this is my ground truth label. So I have a car and a bounding box that exactly shows the location of that particular car. Now, after this region proposal network, okay, your model might have found, say, 4 different boxes. Okay, this is first box. This is the first box. Okay, this is the first region proposal that is given by the network, because there are some part. This part of the car is actually come into box under box 1. So it assumes that it has some objects. And this is second box. It's a very small rectangle. Assume that it also came as a region proposal from your RPN network. And this is box 3. Okay, box 3. It's a larger area is covered by box 3, and this is box 4. So assume that your RPN produces these 4 predictions or these 4 bounding boxes. Now, ultimately, what we have to do as a model, the model are supposed to pick the best box possible. Okay, the best box that captures the whole object. So there comes the idea of IOU, that is intersection over union. So this IOU is calculated as area of intersection divided by area of union. So for each of the box with respect to your ground truth box, definitely you will have a ground truth box. So you will compare, the model will compare box 1 against this ground truth box, and an IOU value is calculated. So all this is being, will do, the MRCN model will do. Okay, but this is how exactly it is happening. So it will calculate the IOU value. If the IOU value is above 0.5, which is then given to the next module. So in this particular Jupyter notebook, I'm going to show how to use this mask RCNN to perform a image segmentation, instant segmentation. So I'm going with transfer learning. I'm not going to, train my model again. So transfer learning, in fact, it's a very useful technique because, people like us, one of the problem with when we are, proceeding with the computer vision based research, the problem would be resources. So resource in the sense both computational resource as well as the data. So if you have access to the huge amount of data, and if you have enough computational resources, then you can very well go with designing your own deep neural network, train it yourself, and then come up with your own architectures. But another possibility is that we can use what is already existing. So most of the models that I have explained today, starting from lennox to MRCN, most of these networks are already trained on large data sets. One such data set we already discussed, that was ImageNet. We have so many similar data sets, say COCO data set, Pascal data set. So there are a lot of such open image repositories are available, and for all of these models, architectures, the pre-trained weights are available. So MRCN learned on COCONet, that weight is available. ImageNet weights are available. Weights in the sense that actually quantifies the kind of intelligence that the particular neural network has gained out of training. So the weights are available. We can just use them for our own application. So that is what ultimately transfer learning looks like. So today what I'm going to do is the MRCN and transfer learning itself. So the first step is you have to install all the dependencies. So this one I have just experimented in Colab. So the installations were pretty much easy. So if you are using your own local software installations like Anaconda in your local machine, you have to install all these dependencies, say NumPy, SciPy, Pillow, Cython, Matplotlib, etc. So all of them are listed here. Okay, is it in a readable format, the content in the Jupyter notebook, or whether I have to increase its size? Okay, yeah. And then the second step that you have to do is change the runtime as GPU. Okay, because MRCN runs over GPU. So if you're using a Google Colab, you can go to runtime on the top, runtime, and then you can change this, change runtime. I already changed it. Okay, if it is not in, normally it will be in none. So select GPU, graphical processing unit, and save the runtime. Okay, so this first step is install all the dependencies. Second step is you have to change the runtime as GPU. And the third step is check your TensorFlow version. Because I have used the Matterplot implementation of, Matterplot implementation of MaskRCN. So this Matterplot implementation of MaskRCN will work only with certain versions of TensorFlow. It works well with 1.15.2. That's what I found. But normally when it comes to a Google Colab, normally the TensorFlow version would be will be like 2.5 and above. But 2.5 TensorFlow version will not support the kind of MaskRCN and implementation of MRCN from Matterplot. It won't support that. So I've just degraded my TensorFlow by executing this particular statement, percentage TensorFlow version 1.x, just degraded, and then you can just see what is the current version of your TensorFlow. So these are also like a kind of kind of dependencies for some versions of Keras. This Matterplot implementation won't work. So just make sure that everything is is properly installed. And again, these are all dependencies you have to install, and you have to import the required libraries. So next is you have to download, because since we are proceeding with transfer learning, it is better to download and keep your MRCN model, trained model somewhere in your Google Drive. So you can give the location. So maybe if you're if you're using this Google Colab, sorry, I have to import OS here. I'm not going to execute it because I already executed and kept it ready. Because when it comes to this what to say, your Google Colab, okay, the runtime will change. Okay, since I did not use this runtime, it is now I had to restart the runtime. So I have to again do all these installations. I'm not going to show these installations because it will take a little bit time. I'll just give you this Jupyter notebook so that you all can try it yourself, but I'll just explain what and all I did. So this is where you can, give where you are going to store your MRCN model. So in your drive, first you have to mount your Google Drive, and then inside this Google Drive, where you wanted to store. So I have stored this under brain tumor MRCN or Mark RCN. This is where the location that I have given. So give the location. So just to, if you want to give the location, just go to the corresponding folder and then right click copy path and then put it over here. Okay. And then the next step is you have to clone this MRCN library. So which is available in GitHub. So the Matterplot implementation of Mask RCN, this is the GitHub version of that. So you can just download that particular library from GitHub, and then you can fix all the paths. Okay, where is the particular MRCN? Inside MRCN, under samples only, you will have this different pre-trained weights. So this is a COCO data set. So you have so many inbuilt data sets that you can explore yourself. So this particular cell of mine that actually fix all the path, COCO model path, where it is, where is the COCO weights are there, what are all the images. So this, if you press this COCO, you can see the COCO, the trained version of this MRCN on COCO model. So the COCO data set. Okay, so I'll just show now. Once the model path is ready, so this COCO model path is nothing but where you have stored the pre-trained weights. Okay, I think I have my pre-trained weights under Mask RCN itself. Let me see. Yeah. So when you see this mask underscore RCN underscore coco.h5, okay, this is the pre-trained weights of MRCN learned on the COCO data set. So you can download. So all these will get downloaded once you clone the entire Mask RCN library from the GitHub. So you have to give the path to the pre-trained models, and then you are loading your model. Okay. So once the model is ready, so now you have downloaded MRCN library, you have downloaded the pre-trained weights of MRCN on COCO dataset. Now you have to say the COCO datasets, what are all the class names that are there. Okay, this also you can get from their website, COCO dataset class names. And then you can load any image from the COCO dataset. Already the dataset is available in this Mark RCN library. So just load any random image. So you can just, this actually select an image randomly from the COCO dataset, and you can execute. Your output will looks like this. So when you see this result, okay, it was able to locate the objects primarily. So this is first object, there is a bounding box, second object, third object, fourth object. Rest of the image content is considered as the background. Now, along with the object detection, they have some confidence scores. So this actually, it is labeled as, maybe it may not be clear to you. Okay, it is labeled as giraffe with a confidence score of 1. Okay, so 100% the model is sure that this is a giraffe. It is zebra, again, its confidence score is 1. It is labeled as cow with a confidence score of 0.903. And here it's a part, it is again, labeled as giraffe with a confidence score of 0.989. Okay, so this is a custom, this is a random image from the COCO data set. So just to showcase, I just have uploaded a custom image, a vehicle image that I got from the Google search. And I just tested this model. So here, instead of giving a random image, I just mentioned the name of the image, that is vehicle.jpg. So this particular image is also uploaded in my Google Drive. So this particular vehicle image, this is the output that I was able to generate from Mask RCNN. So again, if you can see to this extent, okay, maybe it is beyond it's not, the pixels are not so clear because I've just uploaded a very small image. It's not a high high dimensional image or a a good quality image, maybe because of that. But the model was able to identify most of the vehicles. So it is a car, it is again car with a particular confidence score. So I also have appended a code snippet where you can capture an image through camera. I'm not going to execute it. You can execute yourself. Okay, this will capture an image camera. Probably it will take your photo and you can show some objects in front of your camera, and it will say if it's a part of this COCO dataset. So that's why this COCO dataset classes are there. Okay, it is a person, bicycle, car, motorcycle, aeroplane, etc. So there are a lot of classes which is already being covered in this COCO dataset. If you are showing an object that not comes under this particular labels, then your model may not be able to recognize it. Okay, so with all these classes which are being available in the COCO dataset, that is why, because we have used the pre-trained weights of COCO dataset. So the model is trained in such a way that it will be able to locate, recognize, and segment those objects which are available in that particular dataset. So I hope it is clear. Yeah. So probably with that, I come to the end of the session. So where we started with visual computing. So what is visual computing? Why it is so important? And the session was all about computer vision aspect of visual computing. And then slowly we moved towards the data-driven aspects. Why it is important to have a data-driven model. And then we move towards deep learning, since it is being a part of it's a kind of data-driven modeling itself. And then general deep learning. And then when it comes to your visual applications, okay, you cannot proceed with a normal neural architecture. And then this convolutional neural networks, okay, came into picture. So what is CNN, why CNN, and how CNN works? What are all the different the basic architecture of CNN? And then we have gone through a few classical CNN architectures. Most of them performs well when it comes to a naive application of, say, classification. But when it comes to a real world research problem, then you may not be satisfied with a normal CNN. Slowly, then we move towards the introduction to RCN Family, which is a well-known family for object detection, recognition, and the instant segmentation. And then we had a look into the transfer learning aspect of MRCN. So that's all from my side for today. Let me see whether I have any questions to answer. If you have any questions, I'm open for questions now. Any questions? Yeah, in case if you want to get any further, information, I'll just post my mail ID here, so you can connect me through my mail ID. In case of any clarification or any further, assistance, you can just mail me.
Okay, thank you so much for your wonderful presentation, ma'am. We have learned about the data-driven models on computer vision and the convolution neural network on deep learning, and also the case study on CNN, then transfer learning with Python code. So once again, thank you so much, ma'am. And
Thank you.
ma'am, ma'am, one request, ma'am. Can you switch on your video to take one snapshot, ma'am?
Yeah, sure.
Is it possible?
Yes. Hope I am visible to everyone. Yeah.
Yeah. Just a minute, ma'am.
Thank you, ma'am.
Thank you, ma'am.
Yeah.
Thank you, ma'am.
So I hope no further questions. Okay.
Okay, ma'am. Thank you, ma'am.
Thank you, sir.
Thank you so much. Dear participants, kindly join the next session on at 2:30. Thank you.